Okay, so I told you earlier that whenever I teach this content about climate, the greenhouse effect, and how humans are changing the climate, I told you earlier that I think of this as an argument that I'm having with one of those grouchy old people that rejects climate science, treat this as a matter of belief and say, well, I just don't believe that. Um, I want to finish up that argument today. Um, I want you to be comfortable with this topic. And I don't want you to fall for this idea that it is a matter of belief, because it's really just a matter of understanding, and that's a big difference. If I told you I don't believe in rabbits, you'd say, holy crap, this guy's nuts. Because as far as everybody else would agree, a rabbit is a thing, and if you don't believe me, you can look at how we know it's a rabbit, and then you're like, well, I guess that's how you know it's a rabbit, and then that's a rabbit, and you call it a rabbit. It's got the teeth, it's got the ears, it's got the diet, it's got the little hop, and like, that's nothing else it could be, that's a rabbit. So I want to remind you that climate change is not a matter of belief. This only makes sense when you've seen the stuff that I've showed you so far. And let me remind you that this is the largest scientific topic in the history of humanity, meaning there are millions of scientists all over the world who spent their entire careers on little parts of this science. You understand, right? It's definitely the largest problem ever faced by humanity. It's the most long-term consequences with the biggest impact, not just to our species as a whole, but to the whole planet that feeds and warms us. So it's really solid old science. And I want to show you some stuff, okay, just to wrap up my argument. This will just take a few minutes, but I think that you'll find this compelling. Let me remind you, you already know this, that we understand climate change, we understand greenhouse gases and why they're greenhouse gases, and we understand what variation is natural. We have clear historical records that show both greenhouse gases and temperature, and we have so much data to show that greenhouse gases are going up quickly because of our activity, and to show that temperature is changing. Our whole planet is changing. We have so much data, I want to just really quickly show you that data. You already know about the Keeling curve, and I already told you that we have similar measurements for the other greenhouse gases. So the one on the right at the top is carbon dioxide over a longer time frame. The one in the middle is methane over that time frame, and the one at the bottom is nitrous oxide over that time frame. You can see all of those are spiking in the last 50, 60 years as industrialization has really taken off globally. We have really long CO2 records that show how unique the modern industrial period is compared to 800,000 years of CO2. We know how much this would warm the planet, and if you look for all of that energy, you can find it, mostly in the change in ocean temperature, which of course has caused a measured change in sea level. We have already seen sea level rising. We've seen temperature in the Arctic changing, and the volume of ice in the Arctic going down, because on a hotter Arctic there would be less ice. We can measure the mass of the Arctic's ice sheets going back 1,450 years, and obviously this recent spike that has caused this reduction in volume is a very unique change in the total amount of ice that we have in the Arctic. It's not just ice moving around, weather patterns. This is unique. It's also paralleled by the accelerated rate of loss to Greenland's ice sheets. The ice mass has gone down, and by the way, so has the South Pole. We've noticed changes to these giant deep ocean currents that affect our entire global weather systems. And this helps explain weird little flukes, like why the North Atlantic gets colder on a hot planet. That's not a mystery. That makes sense. It follows to reason. There's these giant ocean currents that were previously mysterious that we now map and understand really, really well. They're all included in modern climate models. We've got measurements of temperature, so many measurements of temperature, pretty much all measurements of temperature, without exception, show that there's something really weird happening recently and that it's unique. Every place you could look for evidence, it all points to the same thing. We have less snow cover, less glaciers, higher surface temperature, higher humidity, higher temperature coming out of the oceans because the ocean itself is hotter and sea levels going up and the temperature over land is going up and the amount of heat in the content in the ocean is going up and the amount of sea ice is going down. Every part of the system where you would predict, on a heating planet, this would be happening, we're finding all of that. And let me remind you that scientists don't just like, yeah, that looks good. We have to include models that help us understand all of this. And, computers have come a long way. Because this topic is so big and so old, the growth of computing has paralleled a growth of science. It's kind of an amazing thing, and a lot of tech nerds study just this topic that's on the screen now. When we first started to model climate, we could only keep track of a couple of variables, a simple equation. And every few years, some science nerd will figure out how to add another variable or two. So we started with rain and CO2, and then we added clouds, and then we added the albedo of land, and then we added the amount of area on Earth, which is ice. Then we added different evaporation rates of water. Then we added the other greenhouse gases. We added chemistry that happens in the ocean and the specific heat capacity of the ocean, to see where all this energy is moving around. And we keep adding variables. The formulas now are pages and pages and pages and pages, each to explain one variable in this huge algorithm, which is these giant models that model our climate. We've got biotic carbon cycling, other types of pollution, natural stuff like volcanoes and stuff. We've got the Milankovitch cycles included. We have river action, which moves water along the surface, which changes temperature. We've got the presence of aerosols in the air, like little particulate stuff. We've got secondary chemistry in the atmosphere included in our algorithms now, interactions with vegetation, the changes in land use, and we're adding, calibration from satellites to make sure that all those numbers are reasonable as the models start to run. We've got real-time data proofing. So like if your model says there should be some wind developing in the North Atlantic, we can measure that and say, yeah, it is that much wind. So then you can go to the next step in the algorithm. And we've got these massive jumps in computation power. These algorithms are so big that you can't run climate models on a single supercomputer. We do what's called meta computing. So a whole bunch of institutions like libraries and governments, science labs and universities, they'll all donate their computer networks at night to contribute to the computing of these huge algorithms in the cloud. So when UCSB goes to sleep, all these computers turn on at night and they're all crunching a part of the algorithm. It's so much data that you can't even house this in single supercomputers anymore. People have graphed all of the ingredients that are included in climate models. And by the way, people have graphed the bandwidth. Like climate modeling today uses more computer bandwidth than military activity. Like it's massive, massive amounts. of detail in climate models in the year 2020. Plus, we used to have clunky models that like treated all of North America as a thing, but models have become increasingly granular. So we run that entire model on like 100-mile block. And then we run another one on the 100-mile block of the air above that, and a 100-mile block to the right of that, and 100-mile. So we're running these models with really fine focus, you know, like adding pixels to an image. It used to look pretty blurry when there was only like 100 pixels, but now we can get like 4,000 pixels per inch. We can get really, really, really tight. And so we can see these really fine impacts. And all models show that nature cannot explain current climate change alone. See, look at the screen here at the bottom. You've got the human causes included in climate models, or the natural variability included in climate models. Let me clarify this. When we model nature, or we include humans, you can tell only one of those explanations captures what we measure. We say that it is attribution. That the only way to explain current changes in climate is the explanation that includes human factors, not an explanation that is natural drivers alone. This type of research is not a single person making a statement. It is an ongoing global effort in different continents, in all the world's oceans, and all the world's land combined. We keep doing this over and over and over and over. Every year we try to find the best models, right? The ones that most closely match what we know is real. So you measure it and then you try to explain it. And whether you break it down to little pieces or you add in the entire world, all models show that nature cannot explain, without humans, what's happening to climate. And it perfectly explains, with humans, that we are the missing detail of what's causing this climate change. That is such a profound statement. When somebody says they don't believe this, it's like, what is the belief part? You know what I'm saying? And I'm just, there's, when people are like, oh, this is not a big deal. Like, bro, how is this not a big deal? There is no model of climate variation that doesn't exist. There is no variable where we're not going to fry in this planet. Different models are either we're going to heat up a little bit now and a lot later, or we're going to heat up a lot now and then a whole lot later. And everybody's like, oh yeah, but the scientific community's divided. Like, no, it's not. We've done so many surveys. Watch this. We know that scientists are not actually divided. If you take all scientists in general, right? Like, let's include engineers and cancer researchers. There's 11% who don't agree that humans are primarily responsible for changing climate. 11% would be like, whoa, that's kind of an interesting debate. But let's just focus on the climatologists. There's about a 1% outlier rate. That looks like pretty clear consensus. Like 99% of people don't agree on a lot. You know what I'm saying? Like 99% of people don't even agree on how to treat cancer within cancer treatment circles. Like 99% is pretty solid. And this wasn't a single study. This has been repeated in other studies. As a matter of fact, there was a study that analyzed the result of climatologist studies. So these fools looked at all these different surveys And the scientific community is not divided. The scientific community is starkly unified. These are studies of all members of the American Meteorological Association. These are the most published climate scientists. This is another one to repeat the most frequently published climate scientists. This was all scientists who write publications about climate. This one was all climatologists combined. This was all members of all earth science faculty, including researchers. That's a huge study. This one was all climate scientists. This one was, again, all members of the American Meteorological Society. That's solid. And then we still got this public that's like, well, I don't know. There's some doubt. And you have to understand where that comes from. That's largely a byproduct of how we know our world. You see, when somebody makes a news story about whether the new Toyota is a cool Toyota, you got to have two people on the news because that would be balanced, right? That's interesting. You got to have the guy who says, yeah, that's a good Toyota, but that would be a boring news story. You look biased. So you got to find the guy that says, no, that's not a good Toyota. And then they get to have a debate, and that's good TV. So when the media reports on climate change, they got to do the same thing. They got to have the guy who says climate change is happening and it's caused by humans, and you got to have somebody who says, no, it's not. And, you know, the petroleum industry, other fossil fuel industries, they keep paying the guys to say, no, it's not. Those are exceedingly well-paid speakers. So if you map our media coverage in the United States, about 72% of total media, and this is a little bit outdated, but about 72% of media coverage of climate change includes, you know, balance, right? That's good. We like that. 72% of news coverage in the United States includes some guy who's like, well, no, I don't know if we're sure yet. And that guy is maybe not as qualified as the other one. This might be a climatologist that represents an international community, and this might be some guy that taught physics until he had a scandal and got kicked out of his job, and then looked for a new job, and then boom, got a job giving these speeches. And that makes for good TV. They have an argument. We want to see that. That's educational. But that really biases our public perception. 74% of Americans are not ready to say that humans are primarily responsible for changing climate now. And that's not really reasonable, scientifically speaking. I mean, they might be really nice people, but prove me wrong. Watch this. Here's how you can finish this debate anytime you want. Prove me wrong. You should probably write this down. Some gases trap and re-release heat. We call those greenhouse gases. That's a principle of physics. You can test this in a high school lab. Number 2, this allows some of the Earth's radiated heat to bounce back toward us. And we understand this because we've been building greenhouses since like the Victorian period, and you can test this every day in your car with the parking lot, sunlight and heat. And we know that humans are adding more of these gases to the atmosphere. You can go collect this data yourself. You can see public data on this topic. And you can either take my word for it, you can read the papers, you can continue to get an education at a university, but those gases that we add are the only possible explanation for the current trends we see. We understand natural climate, and this is not natural climate change. And so humans are warming the planet. I mean, prove me wrong. Go ahead. I'm so ready for this. I've been doing this for 20 years. I'm not any smarter. I'm not a climate scientist, by the way. But I've been challenging my students. Go ahead, just prove me wrong. I am so ready. Like I'm super down to be wrong. I love being wrong. I'm not kidding. That's a thing about me. I like to argue, but I don't like to be stupid. You know, we can argue about how we're going to respond. That's fine. And we can argue about how much we care, but I don't think that we can treat science as a belief system. It's like going onto a bridge and cutting the wires because you don't believe in engineering. Like, come on, bro. That's stupid, and you're going to hurt someone. It's like, oh, I don't believe in mechanics, and you'd like take the brakes and the seatbelt and the airbag out of your car. Like, bro, that's just sloppy for you, but that also could have impacts on other people, you know. Like, let's be a little bit more reasonable for a minute here. All forecasts show heating. There's no forecast that doesn't. If humans were to leave the earth miraculously in the year 2000, we would still get continued heating for 450 to 600 years. There's this like simple equation, which is really tough to argue with, that total CO2 is a function of how many people, what kind of services they get, how much energy it takes to give those services, and how much CO2 is made for those energies. And the number of people keeps going up. The number of services given to each of those people keeps going up. And that's not a bad thing. We don't want humanity to live in ugly poverty. And so all of those services require energy. And right now we keep using CO2-based energy. So there's really no way to avoid the CO2 going up until we change one of these. And getting rid of the people is not ethical, and keeping them, you know, in lower service life, in life that is uncomfortable and harmful, is horrific. We could never make that argument. And we know that it's going to take energy to give them those services. So until we get away from the CO2 for energy thing, there's no way to get away from CO2. What's interesting is this is fixable today, like current technology. Like, we don't have to wait for the future. Remember the 15 wedges. And I got to remind you that the College Board always asks about solutions. So don't forget the 15 wedges. All right. I know I'm not arguing with you, but there's like a person out there that I keep arguing with. I don't know, maybe you getting to see that will help you have the argument when you need to have that argument. I don't know.